Welcome to section 2.6, Asymptotic Properties of the OLS Estimator. In the previous sections of chapter 2, what we did is we assumed that the epsilons followed a parametric distribution. Specifically, we assumed that they followed the normal distribution. And if the epsilons are normally distributed, then that means that we can compute the exact distribution of test statistics regardless of how small the sample that those statistics were based upon is. However, if the epsilons do not follow a known parametric distribution, then unfortunately the small sample statistical properties of these test statistics that we have computed are unknown. The properties of B are unknown. But in such cases, we can evaluate the properties of B as the sample size becomes infinitely large, and that's asymptotics. Much of asymptotic theory is based upon Chebyshev's inequality. And Chebyshev's inequality tells us for a random variable z, the probability that the deviation of z from its central tendency or mean value, the probability that that deviation is greater than some positive delta is strictly less than the variance of z divided by delta squared for all delta positive. And of course that's in Verbeek's text, equation number 2.67. We can apply this to our OLS estimator B, or more specifically, B is, you recall, a vector of the OLS estimates. So we will say that we apply Chebyshev's inequality to any one of the OLS estimates, and we'll just denote that as B sub lowercase k. So the probability that the deviation of B sub k from its true population parameter is greater than some delta must be strictly less than the variance of B sub k divided by delta squared for all delta positive. Now, the variance of B sub k is given in equation 2.68. We've covered it already. Sigma squared is, you recall, the variance of epsilon, and C sub kk Verbeek defines as the kth diagonal element of x prime x quantity inverse. That's using the full matrix notation. But if you would prefer to use Verbeek's hybrid notation, what we would say is it's given by this second expression, the sum I equal 1 to n of xi transpose quantity inverse. Now, as the sample size approaches infinity, each element of x prime x also approaches infinity. And what that means then is that elements of x prime x quantity inverse approach 0. Right? So, and the way you could think of that, when you look at how x prime x is computed, again using Verbeek's hybrid notation, you could simply think of it as the sample size grows large, each element of x prime x is going to explode. Okay. Now, asymptotics. To evaluate the asymptotic properties of B, we will start as we did earlier when we developed small sample properties. We'll first do some algebraic manipulation to decompose the OLS estimator B into the population parameter that we're attempting to estimate, and leftover, or as I like to call them, the junk terms. So as before, we were able to do that by first substituting in the definition of y, breaking the parentheses, and then of course you notice in the first term on the left we have x prime x inverse x prime x. So we're multiplying x prime x by its inverse, which gives us the identity matrix. So this simplifies ultimately into beta plus the leftover or junk term, x prime x quantity inverse x prime epsilon. Now we're going to do one additional modification to this equation that's going to help us with asymptotics. So to introduce the idea of what happens as the sample size goes to infinity, what we're going to do with the junk term is we're going to multiply and divide by n. And of course, both simultaneously multiplying and dividing by n doesn't change the value of that second term. So in the first part, I multiply by n. The way that operationalizes here, once I take it inside the inverse of the large round brackets, multiplying by the inverse of 1 over n is, of course, equivalent to multiplying by n. Now, and then finally, we'll introduce Verbeek's. We'll go from full matrix notation to Verbeek's hybrid notation, which again introduces this idea of a sample size. So, and then again, just to remind you, you remember xi transpose is defined as a row vector of the ith observation of the X matrix. So it contains 1, x2, x3, x4, etc. up to x sub capital K, and it would be the ith observation of that. Now, if I multiply out these terms in Verbeek's hybrid notation, this is what I now receive. Right? So the elements of x transpose x, or x prime x, are given by the matrix on the left. And what you'll notice is in the northwest, or the upper left-hand corner, that element is equal to the sum from I equal 1 to the sample size of the number 1. So that's equal to n, and n times 1 over n is, of course, equal to 1. So asymptotically, that first element is, in essence, 1. And then you'll notice as I go across the top row of that first matrix, each element is, in essence, the sample mean of x2, the sample mean of x3, etc., up to the sample mean of x sub k. And since this is a symmetric matrix, that means that the column, the first column, is equivalent to the first row. The remainder of the matrix, as I go down the diagonal, that is 1 over n times x2i squared, x3i squared, etc. And the off-diagonal elements represent covariances. The matrix on the right-hand side now becomes the average of the population stochastic disturbance terms, and then the average of the population stochastic disturbance terms time multiplied by each of the other explanatory variables. Now we're going to add a new assumption for evaluating the OLS estimator, its asymptotic properties, assumption A6, which says that as the sample size goes to infinity, the limit of 1 over n times x prime x converges to this matrix, which is finite and non-singular. And Verbeek denotes that as sigma sub xx. It's a finite matrix, meaning that none of the elements of sigma sub xx explode. None of them become large. And also, non-singular means that the matrix is of full column rank, or an inverse exists. So when I compute the limit of x prime x, or 1 over n times x prime x, and I think about what happens as the sample size goes to infinity, since each one of those elements in the first row and the first column represent sample, they represent sample means. As the sample becomes large, those means converge to the population mean parameters. So on the right, you see convergence to mu2, mu3, mu4, etc., up to mu sub capital K. Down the diagonal, 1 over n times the sum of x2i quantity squared converges to the variance plus the mean squared. And it would be, and the relatively easy way to show this is that think about the sample analog, or the think about the definition of a variance, right? The variance is the expectation of x minus its expected value squared. And if you manipulate that identity, you can easily show how the expectation of x squared is equal to the variance plus the mean squared. Okay, so that's how we get the diagonal elements, and then the off-diagonal elements represent, of course, covariances. So this gives me sigma sub xx, and if sigma sub xx is finite and non-singular, then the inverse exists. It's a theorem from linear algebra that I'm sure you all remember. The second assumption, the new assumption that we're going to add, assumption A7, is that the expectation of xi epsilon I is equal to 0. Okay. So this differs a little bit from the Gauss-Markov assumptions that we made early when I think that was in chapter or section 2.3. This is a somewhat weaker assumption, and actually later in today's lecture we're going to compare the stronger assumptions we made earlier for the Gauss-Markov conditions versus this assumption in A7. Okay, so what this says in essence is that the ith observation of the explanatory variable and the population stochastic disturbance term are independent or uncorrelated. Okay, so if assumption A7 is true, then that implies the limit as the sample size goes to infinity of that matrix on the right-hand side from the previous slide. Each element of that is going to be 0, right? So, yes. Now, notice that this condition that we've just developed looks very similar to the OLS normal equations from earlier in the term, but I'd caution you to see the very important difference between the two. The OLS normal equations, which are given at the bottom of this slide, you remember where those came from when we computed the OLS estimators. The way that was done is by differentiating the sum of the squared residuals with respect to each of the OLS parameters, B1, B2, B3, etc., up through B sub k. And then the values of those parameters, B1 through Bk, were chosen to ensure that this condition was met. Right, that the sum of the regression residuals is equal to 0, and the sum of the product of the residual and each of the explanatory variables was 0. You'll notice that this condition right above it is an equivalent condition in the stochastic disturbance population terms. Okay, so similar but different in an important way. Now, if we consider what the limit of b is as the sample size approaches infinity, we'll borrow that term from a couple slides back, and we'll consider what happens as the sample size goes to infinity. Well, borrowing from the previous slides, of course, beta is a non-stochastic constant, so as the sample size goes to infinity, the value of beta is not affected. The next term, 1 over n times x prime x quantity inverse, remember, by assumption, that collapses, or it converges to the value sigma sub xx quantity inverse, which is a finite and non-singular matrix. And then the term on the far right converges to a vector of zeros. So a finite non-singular matrix multiplied by a vector of zeros is itself a vector of zeros, and we get then that the limit as the sample size goes to infinity of b is beta. Then we can say by Chebyshev's inequality that the limit as the sample size goes to infinity, that the probability that b, the deviation of b from beta is greater than some positive scalar delta is 0 for all delta positive. Or if we wanted to restate this in words, we would say asymptotically the probability that the OLS estimator deviates more than delta from the true parameter is 0. So going down the food chain a little bit more, we could say alternatively, or more simply, that the probability limit of b is beta. Or b is a consistent estimator of beta. Now, you remember that earlier in this chapter, when we were talking about small sample properties, we were saying that b is unbiased if the Gauss-Markov conditions were met. Okay. Unbiased, you remember, was a small sample property, and those but here we're talking about large sample properties. Consistency is a large sample property. It's saying that as the sample size goes to infinity, b it consistently estimates beta. Or my words, if we want to really go down the food chain, my words would be asymptotically the distribution of b collapses upon beta. So you have this sequence of bell curves, right, probability density functions, and as the sample size increases, the distributions become narrower and taller, and the distribution of b collapses upon the vertical red line, which is beta, the value that we're attempting to estimate. So that's the picture of what it means when we say the probability limit of b is beta. Now, the properties of probability limits, one that's worth bringing up and emphasizing, you remember when we were talking about expectations, which are again small sample properties, that it wasn't possible to take the expectation of a quotient, right? The expectation of y over x, where y and x were both stochastic, did not exist, or we couldn't say that it was the ratio of the expectations. However, the probability limit of a quotient is equal to the quotient of the probability limits. I'm probably going off script, and this is dangerous, but the intuition behind this, remember that an expectation is a small sample property, and you could say, if I were attempting to derive the properties of y over x, even though x had, let's say that x had an expected value or a mean that was different from 0, but the problem is that, that because x is stochastic, if you have a small sample, you know that quotients become very unstable if x is flirting with the value of 0, right? So if you have a quotient and the denominator is 0, what that can cause is wild swings in the value of the quotient. Right? However, as the sample size goes to infinity, you remember from the previous slide, what happens is the value of both the numerator and the denominator are collapsing, right? That they are converging to their central tendency with certainty. And because of that, we can evaluate the probability limit of a quotient. If the probability limit of b is beta and g is a continuous function in the neighborhood of beta, then the probability limit of g of b is equal to g of beta. And the neat application of this is that if the probability limit of s squared is sigma squared, then the probability limit of the square root of s squared is sigma. And Verbeek cautions us that this property does not hold in small samples. And the reason is that the expectation of s quantity squared is not equal to the expectation of s squared. Yes. Now, under assumption A6 that sigma sub xx is finite and non-singular, then we can say that the probability limit of b minus beta is equal to sigma sub xx quantity inverse times the expectation of xi epsilon I, which shows that the OLS estimator is consistent if and only if assumption A7 is met. That was the necessary condition for consistency. Or expressed differently, the error term is mean 0 and uncorrelated with any of the explanatory variables. And again, note carefully that we're talking about the population stochastic disturbance term, epsilon, and not the regression residual E. Note that the expectation that epsilon I conditional upon xi equals 0 does imply that the expectation of xi epsilon I is equal to 0, but the reverse is not true. Right? A7 does not imply that the expectation of epsilon I conditional upon xi is equal to 0. Right? So assumption A7 is a weaker assumption. The OLS estimator B is consistent given assumptions A6 and A7, which are much weaker than the Gauss-Markov conditions. We covered the Gauss-Markov conditions in section 2.3 of the text. The Gauss-Markov conditions, you recall, were necessary to show that the ordinary least squares estimator was the best linear unbiased estimator. These conditions, A6 and A7, are the minimum conditions necessary to show that as the sample size goes to infinity, B collapses upon beta. Okay? So the conditions necessary to show consistency, which is a large sample property, are much weaker than the conditions that are necessary to show that OLS is a minimum variance unbiased estimator. Now, on to asymptotic normality. B minus beta from the previous couple slides is equal to this expression. Asymptotically, the first piece converges to a finite non-singular matrix sigma sub xx quantity inverse, and the second piece converges to a vector of zeros. But if this expression is multiplied by the square root of n, what happens then is that this expression now converges in probability to a normally distributed random variable. Right? The first piece converges to the finite non-singular matrix sigma sub xx inverse, and the second piece converges in probability to the normal distribution. So, in a finite sample then, what we could say is that B is distributed asymptotically normal with mean beta and variance sigma squared multiplied by sigma sub xx quantity inverse divided by the sample size n. Sigma sub xx is unknown, right? But we can consistently estimate it by a sample analog. And we use, again, Verbeek's hybrid notation to illustrate exactly how that would be done. So this would be the approximate distribution. You'll notice that in 2.76, as compared to 2.75, we have substituted s squared for sigma squared, and we've substituted the sample analog for sigma sub xx quantity inverse. Now, T and F tests, which remember had exact distributions if we made parametric assumptions for the distributions of the epsilons, now we can say that T and F statistics are approximately valid even if the errors are not normally distributed. Right? So for large enough samples, we could say that the results hold asymptotically, or for sufficiently large samples. So we can say that this T statistic is approximately standard normal under the null hypothesis. The multivariate test statistic for linear hypothesis, RB minus Q with J restrictions, and this was a result we had from a couple lectures back, is now approximately chi-squared with J degrees of freedom under the null hypothesis. Now, you remember one of the Gauss-Markov assumptions, assumption A2, was that the epsilons and the x's are independent across all elements of the sample. We have, so assumption A8 significantly relaxes this assumption. Notice that what A8 does in contrast to A2, A8 says that the explanatory variable and the stochastic disturbance term are contemporaneously independent. But we're saying nothing about how xi and epsilon j might be correlated for some I not equal to j. One example that comes to mind in macroeconomics or finance, empirical finance, it's often quite common to include the lagged dependent variable as an explanatory variable. So, for instance, if we had an equation explaining what the level of gross domestic product was, so one explanatory variable might be gross domestic product in the previous year. So if GDP in 2021 is a function of GDP in 2020, what we could say then is that the explanatory variable, right, the right-hand side variable, GDP 2020, is now correlated with epsilon 2020. So, GDP 2020 may be uncorrelated with epsilon 2021, right? That would fulfill assumption A8. But you notice that since it is a lag-dependent variable, it is correlated, or it can be correlated, with some of the lagged stochastic disturbance terms. So, in an equation such as this, the small sample properties are unknown, but B remains consistent as long as assumption A8 is satisfied. Now, if only the asymptotic properties of an estimator are known, small sample properties are unknown, but they can be empirically evaluated by a randomization or Monte Carlo type studies. And in a Monte Carlo study, a large number of samples are drawn at random and the model is estimated, and you, in essence, build an empirical distribution. And you compare the results from your real data with the randomly drawn randomizations or counterfactuals. Okay. So to give you a simple idea of how this works, what if we had a population which we knew with certainty was normally distributed with a mean of 0 and a variance of 100. So X is distributed normally, mean 0, variance 100. And suppose that a researcher draws a sample of 100 and computes X bar. Now, we know that that X bar will be distributed normally. We know that it has a mean of 0 because the underlying distribution of X also has a mean of 0. We know that the variance of X bar is going to be equal to the variance of X divided by the sample size. So since both of those are 100, we know that the variance of the sample mean is going to be 1. Now suppose that I was interested in finding the value, the largest negative 3-star result, right? So if I were doing hypothesis tests that X bar is equal to 0, and I were looking for critical values that would cause me to reject the null in favor of the alternate at a 1% level of significance, a two-sided test, the critical value that I would be looking for would be the value from the standard normal distribution that contains 1/2 of 1% in the left tail, right? So that is sigma inverse of 0.005. So that says this is the number of standard deviations that I have to move left of the mean to capture an area of 0.005 in the left-hand tail. Now, we know that for a normally distributed random variable, this value is minus 2.5758. We know this from theory. But to show you how these estimation techniques work, in some sense, this is kind of a stilted example because we know in theory what the correct answer would be, but then we're going to implement two different statistical techniques for estimating this largest negative three-star result, and then compare them to the value that we know should be generated from theory. So if we ignore what we know to be true in theory, let's first implement conventional small sample techniques. Remember, small sample techniques were dependent upon knowing the distribution of the underlying statistic. And here we do. We know that it's normally distributed. But remember, this is an illustration of what you can do if that is not met. So in some sense, I'm kind of playing it both ways. So suppose I draw a sample of 100 and estimate what that largest negative 3-star result would be based off the sample variance, right? So we know in theory that if the x's are distributed normally, mean 0, variance 100, what we know is that s squared should be 1. But if I estimate s squared off the sample that I draw, the sample of 100, it's going to be close to 1, but it's not going to be exactly so. Right? There's going to be some amount of sample variation. So based off this sample that I've drawn, the sample of 100, I'm going to compute x bar, the sample mean. It ought to be really close to 0, but again, because of sampling, it's going to be a little bit different. And we can compute the sample standard deviation of this mean, right? And we do that in the normal way. It ought to be close to 1, but there will be some amount of deviation. So if I want to compute this largest negative 3-star result, that's F inverse. So F is, of course, sample-based rather than phi, which is theoretically based. So the sample-based largest negative 3-star result, the amount that captures 0.005 in the left-hand tail, it's going to equal minus 2.5758 multiplied by S of x bar, which, and remember, S of x bar was the sample-based standard deviation of x bar. Okay. Now, it turns out that we know in theory what this value ought to be, right? It ought to be minus 2.5758. But because of sampling, there's going to be some amount of variation. And the variance of this largest 3-star negative result value is going to equal minus 2.5758 squared times the variance of this standard deviation. We're really getting deep. But anyway, I computed all these things. I'll show you here in, actually it's going to be the next slide. So contrast this with the Monte Carlo or randomization methods. Right? So in this previous slide, I showed you how you would compute this using conventional small sample methods. But remember, the whole reason for doing a Monte Carlo or randomization study is if we don't know the underlying distribution. We don't know this underlying distribution of x. So what I could do instead is I could draw, so if we take the first line, I could draw 200 samples, right? So I draw a sample of 100 and I compute x bar. I draw another sample of 100 observations, compute x bar, and I repeat that for 200 times. And then I order these means that I've computed from the smallest to the largest. And the first order stat, what that says is when I sort these 200 computed sample means from the smallest to the largest, order stat number 1 would be the smallest sample mean that I've computed. That smallest one out of 200 draws, at least intuitively, you would think, ought to be really close to minus 2.5758, right? It's because remember, to get a 3-star result, a result at a 1% level of significance, what we have to do is we have to put a density of 0.005 in both the left tail and the right-hand tail. So I'm claiming that if we take 200 draws, we compute the sample mean 200 times, the smallest sample mean that I've computed should be a somewhat decent estimator of that. Now, it turns out that order statistics themselves also have means and standard deviations based off asymptotic theory. So the mean and the standard deviation of the first order statistic with 200 draws is given here in the right column. So what you see then is if I have 200 draws and take just the first one, my estimate of the largest value that gives me a 3-star significant result is going to be too small by a fair bit, and it's somewhat noisy. Now, if I take instead 400 draws and look at the second order statistic, so not the smallest one, but the next smallest one, the bias goes down. The bias is actually cut in half, and the standard deviation almost in half. So as I have more and more draws, the accuracy of this method increases. And what you can see is as I get up to 10,000 draws, so remember, this says that I draw 10,000 samples of 100 and compute the sample mean. By the time I get to 10,000 draws, this technique is extremely accurate, right? I'm very close to the value that I know is theoretically correct. So I did it empirically in Stata. Actually, I think we're going to probably spend some time going over randomization methods, so we might talk about these methods in a little more detail. So in panel A, we're comparing the two techniques with 200 draws. Now, my little comment in the far right, the small sample methods here, and those are illustrated by the dashed line, right? That shows the mean and the variance of standard small sample techniques. And the vertical line represents the theoretical truth. That's minus 2.5758. Right? So you'll notice that the small sample techniques here actually do work quite well. The reason why is that the underlying x's are normally distributed, right? So the necessary assumptions were met for small sample techniques to work reasonably well. The solid line represents, I believe I did 1,000 repetitions of 200 draws. Right, so it took gobs and gobs of computing time. So what the solid line represents are values that my computer actually came up with, where I drew 200. So in panel A, I drew samples of 100 200 times, and then I took the smallest mean that was computed. So I repeated that 1,000 times, and then this is the distribution. And remember from the previous slide, what we found is that that this technique had bias with a minimum number of draws of 200. But notice that as I have more and more draws, so as I look at panel B, C, and D, as the number of draws increases, you remember the bias goes away and the standard deviation collapses. So that by the time you look at panel D, the randomization-based methods are really quite accurate, right? You can see how the distribution is collapsing upon the vertical bar. right? The peak more or less goes through the vertical bar, and the accuracy of this largest negative 3-star result is actually quite a bit better than the accuracy of using conventional small sample based statistical techniques. Okay. So in section 2.7, Verbeek gives us an example based upon the capital asset pricing model. So the capital asset pricing model is a classic result from finance based upon the efficient market hypothesis. Right? So this idea that we have full information and a large number of traders and systematic inefficiencies are basically rooted out by arbitrage. So CAPM is an equilibrium model that assumes all investors compose their asset portfolio on the basis of a trade-off between the expected return and the variance of the return on their portfolio. So a higher expected rate of return is good. The variance rate of the rate of return, so that says, is there substantial variation in the rate of return that investors actually have? So if there's less certainty, uncertainty is considered a bad, right? So what investors are doing is they're trading off a good, the higher rate of return, against the bad, which is uncertainty in what sort of rate of return that they're going to earn. So this implies that each investor holds a so-called mean variance efficient portfolio, which gives the maximum expected return for a given variance level of risk. The aggregate of all individual portfolios, the market portfolio, is mean variance efficient. Now, in CAPM, investors can place their money in the risk-free asset. The risk-free asset earns a rate of return R sub F. They could invest their money in a very broad market-based index and earn the market rate of return, and that's R sub M. R sub M. That would be the market rate of return. The rate of return that an investor gets off an individual asset would be given, in this case, R sub J. So let this be the rate of return that security J, so that could be an individual stock, it could be a managed index fund, or a managed fund, whatever. So what 2.77, which is CAPM, is telling us, so if we start on the right-hand side, the far right, R sub MT minus R sub F, this says, this says how much higher is your rate of return if you invest in the stock market versus the risk-free asset, which you remember is assumed to be U.S. Treasury bills. So if I invest in the stock market versus Treasury bills, what is my extra rate of return? And on the left-hand side, we have the additional rate of return that I get from holding an individual stock versus Treasury bills. So what CAPM is telling us is it's estimating, well, I guess I should just read my own text at the bottom here. The expected difference in return for holding asset J instead of the risk-free asset, or the risk premium, is proportional to market risk premium. So you remember the golden rule of finance, that return is the reward for bearing risk. So if we think that higher return is a good or desirable by investors and risk is bad, you remember that in efficient markets, a higher return is the reward for bearing risk. So you get this trade-off between risk and return. Now, beta, so beta sub j, which is given by equation 2.78, you'll notice that that's a conventional OLS slope. It's the covariance of the return on security J and the market rate of return divided by the variance in the market rate of return. So what CAP-M, or equation 2.77, is telling us is that the additional return, or the excess rate of return you get from holding a single asset, is proportionate to the risk that you bear. Right? It's basically operationalizing the golden rule of finance. Now, this previous equation, 2.77, can be modified as a regression model to analyze the rates of return on various stocks or various funds. Now, professional money managers tell their clients that their clients should pay them to manage their money because they can beat the market, right? So this regression equation would be one way of analyzing whether that is indeed true. Is it possible to systematically beat the market rate of return? So we have on the left-hand side the excess of the individual security over the risk-free asset, and it's a function of the excess of the market rate of return over the treasury bill as the explanatory variable. Notice that this is an example of a regression that doesn't have a constant or an intercept, and then when we rearrange the terms from 2.77, then we get the structural components of the stochastic disturbance term epsilon. We're going to assume that the expected, under an efficient market, the expectation of epsilon sub jt is equal to 0. Now, although CAP-M does not have an actual intercept term, one can be added to represent systematic outperformance of the market, and we'll call that alpha. Now, Burton Malkiel, who is this professor of finance, I believe it was at Princeton, wrote this book, A Random Walk Down Wall Street, which was a runaway bestseller on money management. And what Malkiel said in A Random Walk Down Wall Street is that prices in their that security prices in their day-to-day movement were in essence a random walk. So movements day to day, innovations upward or downward, tended to be random and unforecastable. If that is true, Malkiel claimed it was extraordinarily difficult, if not impossible, to systematically outperform the market rate of return. One could do it on maybe a month or two or a year, but it's virtually impossible to do this consistently on a long-term basis, month after month, year after year. Now, when this equation from the previous slide was run, one of the money managers who was evaluated was Bernie Madoff, who was this celebrity money manager. He managed money for very wealthy people, for celebrities, for high government officials. And Madoff, it was discovered probably about a decade ago, was running this massive Ponzi scheme. So rather than actually investing the money, what he was doing is he was taking money that was newly invested with his firm, and he was using that to pay off previous clients and keep some portion of it for himself and for his family's use. So Madoff's Ponzi scheme depended upon getting ever greater amounts of new customers, and hope not to get caught. Well, so when Madoff's portfolio was evaluated using the equation from the previous slide, his estimated beta coefficient was extremely small. So what that meant is that the variation in the rate of return on Madoff's portfolio was actually very small relative to the market risk. Right? It was basically like investing your money in an index fund, but the systematic rate of return, alpha, was 0.5. So in other words, Madoff was consistently beating the market by a large amount, and his customers were bearing very, very little risk. And proper econometricians argued they approached the Securities and Exchange Commission and said, this is simply not possible to do this. It has to be, this has to be fraud. Madoff has to be engaging in massive fraud to be able to generate these kinds of returns year after year while not exposing his customers to risk. And of course, it turned out that it was indeed true. But Verbeek, in his description of this, says that for years the Securities and Exchange Commission ignored pleas that Madoff was a crook. Of course he was. Actually, Madoff passed away in the summer of 2021, just a couple months before I'm making this video. But anyway, it's an interesting application of these sort of techniques in action.